Okay, so now I'm going to prove Bessel's inequality. Now, Bessel's inequality is a very general inequality. That's true. That's true in anything that we call a Hilbert space, which is going to be anything that has something called something that like an inner product. Now, we are of course going to apply it into a very particular situation, but I want to state the theorem in kind of a very general way, just because it's such an important theorem. This is called Bessel's inequality. Um, and along the way, one of the things that the proof of this theorem is going to do is it's going to show us this least squared approximation property. In other words, if I have a set of vectors, a set of orthonormal vectors that span some subspace, and I have some vector or some function that does not necessarily lie in that subspace, how can I best approximate that function using only elements of this subspace? Okay, and of course, two questions need to be asked. What do I mean by best approximation? Actually, that's the question that needs to be asked. What do I mean by best approximation? And then two, well, maybe this is a question, how do I find the best approximation? And Bessel's inequality is going to do both of those things. I don't know, I'll probably have to split this video into two parts. I know the last one was kind of painfully long. I don't want to make this one that long. Okay, so first things first, again, we're going to look at a very general situation. Well, not as general as it could be, but sort of a general situation. So let phi k's be an orthonormal, actually, I'm going to make this now, an orthonormal, so I don't want to write that again, so an orthonormal set of functions on minus pi to pi relative to the inner product given by the following formula. The inner product of f and g is 1 over pi times integral from minus pi to pi, minus pi to pi, f times g. That integral. Okay, so for us, the functions that we're going to have in mind are going to be cosine kx and sine kx. They're orthonormal with respect to this, and remember what orthonormal means. It means the inner product of phi k and phi l is going to be equal to 0 if k does not equal to l, and is going to be equal to 1 if k is equal to l. And again, if I divide by 1 over pi, the sequence of functions that we're interested in, sine kx, cosine kx, satisfies this here. Okay, but I'm not really ever going, in the proof that I'm going to be looking at, I'm not really ever going to write this integral. Now, one nice thing that you might be able to do, or one thing that you should do or could do to help you is when you take notes, watch the video once, and whenever I write an inner product like that, don't write the inner product, write the integrals. Then you'll get an idea of what's going on. Write that. Then you'll get an idea of what's going on in the space that we actually care about, which is going to be the space of functions who are square integrable from minus pi to pi. I'll say more about that in a moment. Okay, but I want to keep things like this just because the Bessel's inequality is such a generic and general fact. I don't want that. I don't want this sort of the detail about integrating from minus pi to pi and the 1 over pi. I don't want that to kind of get in the way of things. Now, eventually, when we apply Bessel's inequality in the proof of the convergence of Fourier series, we'll have to have all of this. But just for Bessel's inequality, we don't have to have it. Yeah, and by the way, I haven't said what Bessel's inequality is yet. Okay, so now I'll say that. So what Bessel's inequality says is the following. The sum from k equals 1 to infinity of the inner product of a function f with the phi k's, and I square, so I'm summing up the square of all of these inner products. This is going to be less than or equal to the integral of the square of the function. with a 1 over pi here. Okay, and I actually want to write this right-hand side just a little bit different. And that's what's going to motivate the following definition. So the space L2 of minus pi to pi consists of all, so I'll say why I'm doing the quotes there in a minute, all functions on minus pi to pi such that the integral from minus pi to pi of f squared is less than infinity. Okay, and again, you could put the 1 over pi here. That obviously doesn't change the definition of this space. So L2, I won't write the minus pi to pi. So why do I have all in quotes? Well, this only applies to functions that are called measurable functions. That is functions for which we can define this integral. So I'm not going to say any more about that, but any function that you can think of is going to be a measurable function, unless you know how to come up with to construct a non-measurable function. Okay, so L2. Another way to think about a measurable function is that, well, I'm not going to say anymore, sorry. Okay, so L2 is an inner product space. And basically what that means is that there's an inner product, which we define this way, that induces this quantity right here, which is called the norm of the function, or the square of the norm of the function. It's a measure of the size. Okay, it's like the magnitude of a vector. Okay, so it's an inner product space, so it has an inner product, and what this means is that the norm squared of a function is given by the inner product of a function with itself, or, like, what does that mean in terms of integrals? It's going to be, for us, in this particular case, we can do the modulus squared if we want to also deal with complex valued functions. Okay, so then the norm of a function is just going to be the square root of all of this stuff, like this. Okay, but the point is it's a measure of size. And this type of thing comes up a lot. Well, it's good because we're integrating something positive. We're integrating, if we just look at real valued stuff, then we're integrating something positive. Okay, and why is that? Well, there's not going to be any cancellation in the integral. So if I want to think about, a sequence of functions, Sn of x minus f of x squared, well, the only way this integral can be small is if the thing that we're integrating is getting smaller. So in other words, the better and better Sn of x is approximating f of x, the smaller this integral will get. Okay, subject to all of the caveats we saw in the previous video. On the other hand, if I just have like a 1 there, and I'm just integrating that, well, there could be, like, these two things could be far apart, but there could just be cancellation that happens to cancel out enough to make this small, even though both functions are far apart from each other, right? That's what we get when we have orthogonality. If you do cosine of kx times cosine of lx, you do that integral, the function that you're integrating isn't 0, but there's a lot of cancellation to cancel each other out. Okay, so that's one of the reasons that we prefer to look at the square of the integral. And of course, in our context, we should also put maybe a 1 over pi here. Okay, so in other words, I can write this right-hand side here not as the integral of f, but as the norm squared of f. Okay, and again, why do I want to do that? Because if I look at this inequality, this is a pure fact about Hilbert spaces. And even if you don't care about Hilbert spaces in general, like, if you just want to think about this inner product as representing integrals, that's fine. But now they can represent integrals not just from minus pi to pi relative to the 1 over pi weight, integrals from any interval, as long as the functions are orthogonal. Okay, so I prefer to write it this way, not because I want to be confusing, but because I want to illustrate the general application of Bessel's inequality and the least squared approximation. The least squared approximation thing that we're going to look at is the exact same least squared approximation that you saw in a linear algebra class as well. Only we have infinitely many vectors now instead of a finite number of vectors. Okay, so the last thing that I want to mention, just to kind of set up what we're going to be doing here, is so this is the inequality that's called Bessel's inequality. Okay, and we're first going to start off with the following. So we're just going to look at the first n of these functions. So k equals 1 to n. So we're just going to look at these functions, and we want to find coefficients, so constants, ck, k going from 1 to n, such that the vector or the function, I'll call it f tilde, equals the sum k equals 1 to n ck phi k, such that this best approximates I want to find the sequence of functions, I want to find the sequence of coefficients that best approximates f. I want to find the sequence of coefficients that best approximates f. Now maybe from the look of it, this has nothing to do with this inequality, but just go with me. So, in fact, the main part of the proof is going to be showing which CKs do this. All right, so we want to find the CKs such that this best approximates f. Well, okay, what does best approximate mean? This has many different good definitions, but for us, we're going to have this least squared approximation. So in other words, for us, this means we want to find the CKs that minimize the following: the norm of f minus the sum k equals 1 to n ck phi k. Actually, the norm squared is what we're going to do. Okay, we want to find the CKs that minimize this. So we want to minimize over C1 up through Cn. These are in principle, it could be complex coefficients, but I want to find the CKs that minimize this expression here. So this right here would be f tilde. Okay, so why do I want to minimize this? Well, if f is exactly equal to this, then these two things are equal, and so it's just equal to 0. If f is not equal to this, in other words, if I can't find coefficient ck to make this equality, this is the error in the approximation. And I want this error to be small in this least squared sense. Okay, and this will probably be the last time I do this, but if I write this out in terms of an integral, just so everyone is somewhat, let me write it down here, just so everyone is kind of clear on what I mean by this. If I write this out explicitly as an integral, it's going to be 1 over pi, again in our context, minus pi to pi, f of x minus the sum k equals 1 to n ck phi k of x squared dx. Okay, I want to find the CKs that minimize this expression here. And what I will show in the next video, the claim that I will prove in the next video, this happens if and only if ck is equal to the inner product of f and phi k. Okay, in which case, well not in which, in which case we call this the projection of f onto the space spanned by these functions here. And again, this is exactly like the least squared thing that you saw in linear algebra. Like, go back and look at your linear algebra book. You're probably going to see something like this, except the sum, instead of going to infinity, is only going to go to n. Okay, that's it for this video. In the next video, I'm going to prove this, and then once we have that proven, it'll be pretty easy to prove Bessel's inequality.